Galaxies, and those are typically gargantuan black holes, millions or billions of times the mass of the Sun. Throughout the years, physicists have depended on a combination of theories such as general relativity, quantum mechanics, and the Standard Model to unlock the secrets of our universe. These theories have effectively explained cosmic phenomena, shedding light on how celestial bodies behave and the intricate nature of particles at the smallest scales. Without theories guiding us, there would be so many questions out there in the cosmos that would go unanswered. But what if we've been mistaken this entire time? Brian Greene has finally broken his silence and said that all modern theories are wrong and that we're living inside a black hole. Join us as we decipher what Brian Greene was talking about 0.4 billion years ago, rotating around each other, going near the speed of light, slamming into each other, creating a tidal wave in the fabric of space, and how this discovery can possibly change everything we've ever known about our reality. In the realm of theoretical physics, few voices carry as much weight as that of Brian Greene. No one can deny his exceptional contributions to the field, particularly in the realm of string theory. His depth of knowledge, clarity of thought, and ability to communicate intricate concepts to both experts and the general public have established him as a leading authority in the scientific community. Greene's expertise extends far beyond his remarkable research achievements. He has an extraordinary talent for unraveling the mysteries of the universe through his books, lectures, and media appearances. Through his best-selling works like The Elegant Universe and The Fabric of the Cosmos, he has successfully bridged the gap between the esoteric world of theoretical physics and the curiosity of the wider public. His unique ability to distill complex ideas into accessible narratives for everyone has empowered countless people to engage with profound scientific concepts. In a way, he's also been responsible for growing the scientific community as a whole. But it's Greene's academic background and professional accomplishments that solidify his influential position. As a professor of physics and mathematics at Columbia University, he has mentored and inspired numerous aspiring physicists, fostering a new generation of scientific thinkers. His research contributions in string theory, a framework aiming to unify the fundamental forces of nature, have propelled the field forward and have earned him widespread recognition from peers and experts worldwide. So when a man like this says something, the world listens. And well, he's now said that all of the modern theories we had always looked to for answers are all wrong. We're not just inside our solar system, we're inside a black hole. Everything we've known about our reality is false. And this entire time, we've been inside a black hole ourselves. But how could that be? Could modern theories be this wrong? The concept that our universe may exist inside a black hole has actually been explored by scientists for a while now. Over the years, several theories and ideas have emerged to propose how our universe could be connected to or originated from black holes. One idea put forth by some physicists is that every black hole could potentially give rise to a new universe. This notion is based on the concept of torsion, which suggests that inside every black hole, a new universe is created. According to this perspective, black holes act as cosmic gateways leading to the birth of new universes inside them. Another idea proposes that our observable universe is inside a black hole, which itself exists as part of a larger parent universe or multiverse. In this viewpoint, black holes serve as gateways to other regions or dimensions of spacetime, encompassing multiple universes or realities. The singularity, the infinitely dense core of a black hole, is also seen as a potential source for the birth of new universes. Some experts suggest that the singularity within each black hole could have given rise to our own universe. This idea draws parallels between the initial state of our universe, commonly referred to as a singularity, and the concept of black hole singularities. Another fascinating theory is that our universe originated from a black hole that resides within another universe. According to this theory, when a black hole forms through the collapse of a dying star, a parallel universe is simultaneously born through a white hole located on the other side of a hypothetical wormhole. This idea connects the formation of black holes to the creation of new universes. But that's not all. Some theories actually propose that our universe could exist inside a higher dimensional black hole. This perspective suggests that our universe began as a singularity, a point of infinite temperature and density, similar to how the scientific community characterizes black holes. The idea suggests that our universe is trapped within the event horizon of a four-dimensional black hole. This would mean that we can't even tell that we're inside a black hole, no matter how hard we try. However, this theory goes against everything we know about the way our own universe works, things that we've already studied and proven to modern physics. Modern physics encompasses a range of theories that aim to explain the fundamental nature of the universe, from its largest structures to its smallest constituents. These theories have been developed through rigorous scientific investigations and have provided remarkable insights into the workings of the cosmos. At the heart of modern physics lies the framework of quantum mechanics, which describes the behavior of particles at the atomic and subatomic scales. It introduced a new way away from classical physics, which was based on strict laws and precise measurements. By uncovering the nature of the microscopic world, one of the key concepts in quantum mechanics is wave-particle duality. It reveals that particles such as electrons or photons can exhibit both wave-like and particle-like properties. This means that they can behave as discrete particles with well-defined positions and momenta, but they can also exhibit wave-like characteristics such as interference and diffraction patterns. This duality is captured by the mathematical formulation of quantum mechanics, which uses wave functions to describe the probability distribution of finding a particle in different states. Another remarkable aspect of quantum mechanics is superposition. According to this principle, particles can exist in multiple states simultaneously, a phenomenon not observed in classical physics. For example, an electron can be in a superposition of spin-up and spin-down states, meaning it exists in both states at the same time until a measurement is made, collapsing the wave function into a definite state. Quantum mechanics has revolutionized our understanding of the microscopic world, paving the way for technological advancements such as lasers and nuclear power, which rely on the principles of quantum mechanics. So if you think about it, quantum mechanics explains the world as we know it, but from a microscopic view, that's the building blocks of life. And ever since their discovery, we have known that everything functions in a particular way. That's supposed to be the truth. But that's not all. There are lots of different theories that have always explained the way our Earth is and how the world really works, like general relativity, which describes gravity as the curvature of spacetime caused by matter and energy. It provides a mathematical framework to understand the behavior of massive objects, including planets, stars, and galaxies. The theory successfully explains a range of phenomena, including the precession of Mercury's orbit, the gravitational lensing of light, and the expansion of the universe. But even then, general relativity breaks down in extreme conditions, such as at the center of black holes or during the early moments of the Big Bang, calling for a more complete theory of gravity. But the standard model of particle physics takes things one step further. This is a highly successful theory that provides a comprehensive framework for understanding the fundamental particles and forces that make up the universe. It encompasses three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Each of these plays a major part in the way our universe works. The electromagnetic force is responsible for interactions between charged particles, such as electrons and protons. On the other hand, the weak nuclear force is involved in processes such as radioactive decay and certain types of nuclear reactions. The discovery of the W and Z bosons, carriers of the weak force, has provided strong experimental evidence for the validity of the electroweak theory within the standard model. The strong nuclear force is responsible for holding atomic nuclei together. It's responsible for the interactions between quarks, the fundamental particles that make up protons and neutrons, through the exchange of gluons. Quantum chromodynamics, a branch of the standard model, describes the behavior of the strong force and has been successfully tested in experiments. So the theories we're talking about here aren't mere theories. They've been proven time and time again to be the real deal. Plus, the standard model even predicted the existence of the Higgs boson, a particle associated with the Higgs field. The Higgs field is thought to be the one thing responsible for giving particles their mass through interactions with the field. In 2012, experiments conducted at the Large Hadron Collider confirmed the existence of the Higgs boson, providing even further validation for the standard model. But despite its successes, the standard model still has its limitations too. One significant limitation is its inability to account for the presence of dark matter and dark energy, which are believed to constitute a significant portion of the universe. Dark matter, a form of matter that does not interact with light or other electromagnetic radiation, is inferred from its gravitational effects on visible matter. Dark energy, on the other hand, is postulated to explain the observed accelerating expansion of the universe. Understanding the nature of dark matter and dark energy remains an active area of research in the world of science and is also one of the fundamental building blocks of black holes too. But that's not where the challenges stop. There's also the problem of trying to unify the gravitational force with the other fundamental forces. The Standard Model doesn't include a description of gravity, which is instead described by general relativity, a separate theory. So maybe Brian Greene does have a point. You see, his expertise actually lies in exploring the fundamental laws that govern the universe, from the smallest particles to the largest cosmic structures. His research has contributed to the development of string theory, a theoretical framework that aims to unify the four fundamental forces of nature, including gravity, within a single, coherent mathematical framework. String theory proposes that the basic building blocks of the universe are not point-like particles but rather tiny, vibrating strings. These strings can manifest themselves in different ways, giving rise to the various particles and forces observed in nature. The theory also suggests the existence of extra dimensions beyond the familiar three spatial dimensions and one time dimension. These additional dimensions are compactified or curled up so small that they are not directly observable in our everyday experience. According to string theory, the universe we perceive is just one of many possible configurations or vacua of the underlying strings, each corresponding to a different physical reality. String theory has generated considerable interest and debate within the scientific community. While it offers a promising framework for unifying fundamental forces and explaining the structure of the universe, it remains a theoretical construct with many unresolved questions and challenges. Experimental verification of string theory has proven elusive due to the extremely high energies required to probe the scales where string effects would become apparent. Nevertheless, string theory continues to inspire research and exploration into the deepest mysteries of the cosmos. So maybe Brian Greene has a point. Maybe we have just scratched the surface of what we know about the universe. But let's take a step back and look at the big picture. The whole thing is that it might be wrong about the world, the way it works, and how it is now. Brian Greene, renowned physicist and author, has recently stirred significant speculation with his provocative assertion that all existing theories about our universe are fundamentally mistaken, proposing instead that we may be residing within a massive black hole. This bold statement challenges the very foundation of modern physics, which relies on established theories like quantum mechanics, general relativity, and the Standard Model to explain the cosmos from the smallest particles to the largest galaxies. The implications of Greene's hypothesis are profound, suggesting a radical rethinking of our understanding of reality and the nature of black holes themselves. Traditionally, black holes are believed to form from the collapse of massive stars, where gravity becomes so intense that not even light can escape their gravitational pull. Within these black holes lies a singularity, a point of infinite density and spacetime curvature, where our known physical laws break down. However, Greene's proposal flips this understanding on its head, suggesting that rather than being external observers of black holes, we might actually be embedded within one. This concept is not entirely new in theoretical physics, where speculation about our universe's origins and structure has led to theories involving multiverses, extra dimensions, and even the possibility of universes birthing within black holes. String theory, a theoretical framework that seeks to unify all fundamental forces of nature, including gravity, provides a speculative avenue where such ideas can be explored. It posits that the universe is composed of tiny vibrating strings rather than point-like particles, and that these strings exist in higher dimensional spaces beyond our conventional four-dimensional spacetime. Despite its elegance, string theory remains unproven and has yet to provide testable predictions that could validate its concepts experimentally. This lack of empirical verification has led to debates within the scientific community about the validity and utility of pursuing such theoretical constructs. In the realm of cosmology, the search for answers often leads scientists to confront the limitations of current theories and to speculate on new possibilities. Black holes, once considered cosmic anomalies, are now central to understanding galactic evolution, gravitational waves, and even the potential for time travel. Whether Greene's assertion will stand the test of scientific scrutiny remains to be seen. It challenges physicists to think beyond established paradigms and consider radical new interpretations of the universe's deepest mysteries. For now, the quest for understanding continues, driven by curiosity, imagination, and the relentless pursuit of truth in the vast expanse of the cosmos.